It had been 44 years since Mount St. Helens violently erupted in 1980, leaving behind a battered landscape, ash-covered towns, and a deep fear etched into the memories of all who witnessed it. Since then, the volcano has remained mostly quiet, a sleeping giant nestled among the Cascades, barely murmuring. People moved on. Nature slowly reclaimed the charred forests, scientists continued their silent monitoring, and the public grew more comfortable with the idea that perhaps the worst had passed. But now, in 2025, that illusion is starting to shatter. A series of strange tremors and heat readings are signaling that the mountain might be waking up again. And this time we have better tools, more advanced technology, and a deeper understanding of the forces beneath the Earth. But that doesn't make the situation any less terrifying. The first sign came quietly. In early January, a cluster of small earthquakes rattled the area beneath Mount St. Helens. These weren't powerful quakes, the kind that knock pictures off walls or send people scrambling outside. They were subtle, deep, and consistent. Seismologists noticed that they were happening too frequently to be ignored. Over the following weeks, the tremors increased in number and shifted closer to the volcano's shallow magma chamber. Then came the gas readings. Scientists monitoring vents around the volcano noticed a spike in sulfur dioxide and carbon dioxide emissions, gases that are commonly associated with magma rising toward the surface. What made these readings so unusual was how quickly they increased over just a few days, a possible indicator that something was changing underground. By February, thermal imaging satellites started picking up rising heat signatures within the volcano's crater. These weren't just fluctuations due to weather or seasonal temperature shifts. This was something deeper, literally. The ground temperature was climbing and fast. In some areas, vegetation that had regrown since the last eruption was beginning to wither again due to the intense underground warmth. Scientists began correlating the heat increase with the shallow quakes, and the picture that emerged wasn't comforting. Something was stirring beneath Mount St. Helens. Whether it was a minor readjustment or the buildup to another eruption was still unknown. But one thing was clear: this volcano was no longer sleeping. To understand the full scale of what's happening now, we have to rewind to that catastrophic event in 1980. On May 18th of that year, Mount St. Helens exploded with a force equivalent to 24 megatons of TNT. It was the deadliest volcanic event in U.S. history, killing 57 people, destroying over 200 homes, and leveling nearly 230 square miles of forest. The eruption sent ash 80,000 feet into the atmosphere, coating cities hundreds of miles away. It wasn't just the explosion that shocked scientists, it was the way it happened. A massive landslide, the largest in recorded history, collapsed the north face of the mountain. That sudden release of pressure triggered a lateral blast that flattened everything in its path, catching even the experts off guard. Since then, Mount St. Helens has had minor dome-building eruptions between 2004 and 2008, but none were considered threatening to surrounding communities. Most people stopped thinking about it as an active volcano. After all, it had been decades since the last real threat. This false sense of security is what experts are now warning against. Because volcanoes, like hurricanes or earthquakes, don't follow our timelines. They don't give us precise countdowns. They simply prepare, slowly and silently, until one day they erupt with unimaginable force. And right now, based on all available data, it appears Mount St. Helens may be entering that preparation phase once again. Local authorities are already on edge. In late March, the USGS officially raised the volcano's alert level from green, normal, to yellow, advisory, signaling an increase in seismic and thermal activity. That might not seem like much, but to volcanologists, it's a critical early warning. It means something has changed within the volcano's structure. Gas pressures are building, magma is possibly moving, and conditions are becoming more unstable. What makes this even more concerning is that the data is showing patterns eerily similar to the months leading up to the 1980 eruption. While there's no guarantee history will repeat itself, the resemblance is too close for comfort. The residents living near the base of the volcano have mixed reactions. Some are packing emergency kits, brushing up on evacuation routes, and following updates from the Cascades Volcano Observatory daily. Others, however, are skeptical. They've heard similar warnings before and nothing ever came of it. The mountain's just stretching, one local said in a recent news interview, dismissing the tremors as routine. But that kind of complacency is what concerns emergency officials the most. Because the truth is, the better our monitoring tools get, the more warning we have, but those warnings are useless if people choose to ignore them. And the science is getting better, fast. Today, scientists are using an arsenal of technology that wasn't available 4 decades ago. Ground-based GPS arrays can detect movements of just a few millimeters. Drones equipped with gas sensors and 3D scanners fly directly over the crater, capturing real-time data without putting anyone in danger. Thermal imaging from satellites provides continuous snapshots of heat changes within and around the volcano. And artificial intelligence algorithms are being used to analyze seismic patterns, identifying unusual clusters and possible magma shifts days before they become obvious to human observers. This isn't just guesswork anymore, it's high-tech forecasting based on hard evidence. One of the most fascinating aspects of Mount St. Helens is how closely it's studied. It's considered one of the most well-monitored volcanoes in the world. The Cascades Volcano Observatory in Washington is practically its shadow, constantly collecting, analyzing, and distributing information to scientists, emergency responders, and the public. What they're seeing now is consistent. There's undeniable movement beneath the surface. Whether it's a slow pressurization or a rapid magma ascent is still unclear, but either scenario means increased risk. And in volcanology, increased risk usually translates to increased urgency. So what would an eruption look like today? Would it mirror the 1980 disaster, or would it follow a different, possibly even more dangerous pattern? Experts are split. Some believe it could be another dome-building phase, relatively slow, manageable, and largely contained within the crater. But others warn that if the magma has accumulated in a more volatile form, or if there's a sudden shift in underground pressure, we could be looking at another explosive lateral blast. And that type of event wouldn't just devastate the immediate surroundings, it could send ash across states, cripple transportation systems, and affect air quality for millions of people. Let's not forget that the Pacific Northwest isn't just home to Mount St. Helens. It's part of the larger Cascadia volcanic arc, one of the most geologically active regions in the United States. Nearby volcanoes like Mount Rainier, Mount Hood, and Mount Adams are also being watched closely. Activity at one could indicate broader tectonic changes that affect the entire region. And since this area sits on the Cascadia subduction zone, a fault line capable of producing magnitude 9 earthquakes, the implications go far beyond a single volcanic event. What we're dealing with here could be a chain reaction, and Mount St. Helens might just be the opening act. In light of all this, the government has begun mobilizing response strategies. FEMA is coordinating with state and local agencies to review evacuation protocols, update public awareness campaigns, and prepare supply caches. Schools in the surrounding counties are conducting volcano drills, something that hadn't been done in over a decade. Hospitals are reviewing mass casualty procedures. Even the airline industry is on alert, as volcanic ash poses a serious threat to jet engines. If an eruption were to occur, air traffic from Seattle to San Francisco could be disrupted within hours, costing millions and endangering lives. But perhaps the most sobering realization is that despite all this preparation, nature remains unpredictable. We can measure gas emissions, track ground deformation, and model lava flows with advanced computers, but none of that guarantees we'll be ready when the eruption comes. In 1980, despite visible warning signs, many people refused to evacuate until it was too late. Some believed the eruption wouldn't happen. Others thought it would be smaller than predicted. And a few simply didn't want to leave their homes. That human element, the unwillingness to act in the face of uncertain danger, is still a major obstacle today. So now we face the question, what happens next? The signs are there. The experts are sounding the alarm. The technology is better than ever. But unless we listen, really listen, Mount St. Helens might once again catch us off guard. This isn't about sensationalism or fear-mongering. It's about respecting the power of the planet we live on. Because the Earth doesn't care about our schedules, our cities, or our disbelief. When it's ready to move, it will. And the only thing we can do is be ready when it does. If you found this breakdown insightful and want to stay ahead of natural developments that affect our world, don't forget to subscribe and turn on notifications. Because the more we understand Earth's warnings, the better chance we have of surviving them. The science of volcanic reawakening is both fascinating and deeply unsettling. Why does a volcano suddenly stir after decades of silence? To understand what's happening beneath Mount St. Helens, we need to examine the immense forces at work beneath Earth's crust. Volcanoes are powered by deep geological processes, slow, invisible, and relentless. These forces include the movement of tectonic plates, the rise of molten rock from the Earth's mantle, and the buildup of pressurized volcanic gases. Mount St. Helens is located directly above the Cascadia subduction zone, one of the most geologically active and dangerous fault lines on the planet. Here, the Juan de Fuca plate is diving underneath the North American plate, creating intense friction and heat. As the subducting plate sinks into the mantle, it melts and forms magma. This magma rises slowly and collects in chambers beneath the volcano. Usually it stays trapped or cools over time. But sometimes the pressure becomes too great. The system destabilizes, heat intensifies, gas builds, and the rock begins to fracture. Magma finds pathways through these cracks and begins to move upward. This upward motion is often driven by volcanic gases like water vapor, carbon dioxide, and sulfur dioxide, which expand as they rise. It's a bit like shaking a soda can and popping the tap. The pressure inside the magma chamber drops, gases expand rapidly, and the eruption follows. This exact chain of events occurred in 1980, leading to one of the most devastating volcanic eruptions in U.S. history. Now, scientists believe the mountain may be heading toward a similar phase. So how do scientists know all of this? How are they monitoring what's happening deep underground? Enter the U.S. Geological Survey (USGS) and its Cascades Volcano Observatory (CVO), a high-tech command center based in Vancouver, Washington. This facility is just 50 miles from Mount St. Helens and operates like a volcano's version of NASA's Mission Control. Inside, scientists monitor dozens of screens filled with real-time data. These come from instruments installed directly on and around the volcano, over 30 seismometers that detect the tiniest tremors, tilt meters that sense even the slightest ground deformation, and GPS arrays that track movement down to millimeters. These tools provide constant updates on what's happening beneath the surface. Gas sensors are also critical. They detect changes in volcanic gases like sulfur dioxide and carbon dioxide, often the first indicators that magma is moving. Thermal cameras offer another layer of insight, detecting temperature shifts that signal new heat sources below the surface. According to Dr. John Major, one of the lead scientists at the CVO, we monitor this volcano every second of every day. The observatory recently raised its alert level from normal to advisory, signaling that a shift is occurring. While this doesn't mean an eruption is imminent, it suggests the system is becoming increasingly unstable and needs close observation. What makes this moment in history different is the technology we now have. Back in 1980, scientists relied on basic instruments, many of which were easily damaged or failed to detect early signs. Today the game has changed dramatically. Drones equipped with 3D scanners, gas detectors, and thermal imaging devices are now routinely flown over the crater. These machines can gather precise data without putting human lives at risk. They can fly into areas too dangerous for scientists, collect samples, and return with invaluable information in real time. It's like sending scouts directly into the belly of the beast. Satellites are another major tool in the arsenal. NASA's Earth Observatory and the European Space Agency's Sentinel-1 mission provide high-resolution radar and thermal imagery of Mount St. Helens every few days. By layering these images over time, scientists can create time-lapse visuals that reveal subtle changes: swelling, cracking, heating. Recent satellite data shows consistent ground uplift in the crater region, paired with increased heat emissions. That's a clear signal that magma is on the move. Even with all this advanced technology, there's still a sobering truth. We can't predict the exact moment an eruption will occur. Despite our best efforts, nature holds the final say. This leads us to a vital question: are we truly prepared for another major eruption? On paper, the answer is yes. Since 1980, emergency management systems have come a long way. Local governments have created detailed evacuation plans. Schools regularly conduct volcano drills. FEMA and the USGS have established protocols for rapid response. But the reality on the ground tells a different story. A 2021 survey by the Washington State Emergency Management Division revealed that only 43% of people living within 50 miles of Mount St. Helens had any kind of evacuation plan. Even fewer had supplies ready to last more than 3 days. It's a troubling level of complacency. Why such low preparedness? One reason is the passage of time. After decades of calm, it's easy to forget the danger. People build homes, raise families, and go about their lives with little thought of the mountain looming nearby. But history has shown us that eruptions can come with little warning. In 1980, some residents refused to evacuate, believing the danger was overstated. They paid with their lives. Today's scientists can issue alerts and recommend action, but it's up to individuals to take those warnings seriously. When the ground shakes and ash darkens the sky, hesitation can be fatal. Preparedness is a race against time. If Mount St. Helens erupts again, what happens in the first 30 minutes could determine the outcome for thousands. Emergency officials have mapped out evacuation zones and identified key transportation routes. But these routes often pass through hazardous terrain: floodplains, forests, steep mountain roads. A full-scale eruption could produce ashfall, lahars, volcanic mudflows, and pyroclastic flows that block roads in minutes. According to FEMA's Region X office, more than 250,000 people live within 100 miles of Mount St. Helens. An eruption could disrupt flights from Seattle to Portland, contaminate water supplies, and cripple the power grid. This isn't just about rural mountain communities. The impact would ripple across the entire Pacific Northwest. Infrastructure, economy, and daily life could be thrown into chaos. In fact, internal documents from the Washington State Emergency Management Division classify Mount St. Helens as a Tier 1 catastrophic threat, alongside major earthquakes and dam failures. That's not an exaggeration, it's a realistic assessment of the volcano's destructive potential. The mountain is no longer viewed as just a beautiful geological feature. It's a ticking time bomb with national-level consequences. So why are scientists sounding the alarm now, after 44 years of relative peace? The answer lies in the data. In the past, many eruptions caught people off guard because we lacked the technology to detect early warning signs. But today we can monitor the Earth with unprecedented precision. Seismic sensors reveal earthquake swarms, often a precursor to magma movement. Satellite imaging shows ground deformation and thermal hotspots. Gas emission detectors pick up on rising levels of sulfur dioxide and CO2. Computer models simulate how magma might behave under different conditions. In recent months, all these indicators have been lighting up. Earthquake swarms have been detected beneath the volcano's southern flank. Ground uplift has been recorded using both GPS and radar systems. Gas emissions have spiked, and heat levels inside the crater have noticeably increased. There have even been slight changes in groundwater chemistry, suggesting that the subsurface is heating up. A March 2025 report from the USGS concluded that these combined factors point to a reactivation of the magmatic system beneath Mount St. Helens. This isn't speculation, it's a clear, data-backed assessment. And it's not just US scientists who are concerned. Experts from countries with their own volatile volcanoes, Japan, Chile, and Italy, are reviewing the data and urging action. There is a growing global consensus among volcanologists that Mount St. Helens is entering a new active phase. This isn't alarmism. It's scientific vigilance. The mountain is stirring, and every tremor, gas burst, or heat spike brings us one step closer to a potential eruption. Ignoring these signs would be not only irresponsible, it could be catastrophic. But let's look beyond the eruption. What might the Pacific Northwest face in the aftermath? That depends on two factors: the severity of the eruption and how well we prepare for it. In the best-case scenario, pressure releases gradually. A lava dome forms quietly inside the crater, much like in the early 2000s. Ashfall is limited and no lives are lost. Recovery takes months, but the region bounces back. In the worst-case scenario, a lateral blast, like the one in 1980, devastates nearby towns. Lahars bury valleys. Trade routes are severed. Airspace is shut down. The region enters a humanitarian and economic crisis on par with Hurricane Katrina or the COVID-19 pandemic. Yet even in destruction there is renewal. Forests will regrow. Wildlife will return. Volcanic ash, though destructive at first, enriches the soil over time. Humans, resilient as ever, will rebuild. This cycle of eruption and recovery is the story of Mount St. Helens. It's not a monster or a myth. It's a living, breathing part of our planet. One that occasionally screams to remind us that we are never truly in control. Our only choice is to listen, to prepare, and to respect the forces beneath our feet. If you want to stay updated on future developments, understand the science behind our changing Earth, and explore the hidden risks lurking beneath the surface, make sure to subscribe and turn on notifications. We've only just begun to uncover what the Earth is trying to tell us, and this is a story that's far from over.